Okay. Yeah. Okay. So again, if anyone wants to contribute to the discussion, just raise your hand or make a question, and we'll be more than happy to answer that question for you. The paper that we're going to talk about today is called "Frustratingly Simple Few-Shot Object Detection." It was recently presented at ICML, so it's again fresh out of the oven. For those of you who have already read the paper, you may have noticed that it is not a particularly complex paper. They don't do a massive contribution, but I thought it would be an interesting way to introduce a topic that we have not discussed about very much in Paper Club, which is object recognition and object detection. And hopefully this will serve as a good paper to get the discussion started. At the end, there is going to be a short poll if you where we're going to ask if you're interested in speaking more about object detection. And yeah, so if you stay to the end and you want to see more papers about this topic, then please just say so. Yeah, so since we have not done very much object recognition in Paper Club, I thought I might start this paper with a bit of an introduction to what the problem is. It's a very interesting problem in machine learning, and it has led to some really funny memes, such as this one. And this, in a nutshell, summarizes what the problem is. You want to, in an image, you want to draw a bounding box over an object, and then you want to classify the object. This is obviously the wrong classification. So the data sets that are normally used look like this. This is the Pascal from Oxford, and then there's the Coco and Elvis data sets, where you have an image, and you can see that the task that the model needs to learn is actually a twofold task. It needs to learn how to draw bounding boxes over objects, and then it also needs to learn how to classify those objects. Why is this important, or why is this useful? Well, for one, if you want to see where all the donuts are in the shop, you can have an AI model tell you where all those donuts are. But there are also perhaps more interesting tasks that you can do with it. One, for example, is object detection for self-driving cars. They rely on these kinds of models to recognize where are pedestrians or where are road signals and draw bounding boxes on them. So if a pedestrian goes in front of the car knows how to brake. There are also very interesting applications in robotics or in AI models for consumer interaction, where you can have, for example, a user say something into a machine that converts then into text, and then that text is fed into the algorithm, and you can ask, for example, where can I find X in an image, and then the model can learn to recognize that object. So if you want to ask a machine learning algorithm, where can I find pineapples, then you just ask it, and then it'll process it and find the pineapples in the image. So in a nutshell, that is the learning task at hand, and it's a very interesting computer vision problem, and it's one that gained traction mainly in the mid 2010s, so around 2014, 2015, because it is a twofold task, and ideally we want one network to do both things. It's a really complex problem. So I'm going to do a quick overview of the architectures, because I think they are a bit needed to understand what this paper is doing, because it relies almost entirely on all architecture. And I think this bird's eye view is also going to show one of the nicer things about this area of research, which is that they use really funny names to name their papers. So just to get started quickly, the whole object recognition really took off with RCNNs, which are CNNs on region proposals. And the novel thing about this is that, well, assume you have another system that can recognize where there are objects, arbitrary objects in an image. They proposed this method to warp those proposals, so those region proposals, and then use a CNN to classify the regions. Now, of course, this was 2014. So of course, this was the very start of these trend of algorithms, and you can immediately see problems with it. So for example, that you have two systems, one that needs to propose regions and another one that classifies those regions. And then you need to classify each of the regions. So of course, this was a system that was very slow to train, but it already started having very good accuracy. So the improvement to this was fast RCNN. So they were not very creative with the name, because what this paper proposed was basically a faster alternative to RCNN. And what they said is that, well, you already have you still have your projection algorithm, but now you can integrate it to your convolutional network. So you have something that can, sorry, not your projection, your region proposal. Your region proposal, you can integrate it with your convolutional network, and you project. So you do a max pooling layer on those regions, and now you can classify all the regions at the same time. Because you lose some of the information about the region when you do this max pooling, what was really novel about this network is that they put both tasks into a single network. So you have a softmax output that tells you which class is more likely to be in the regions of interest, and also a regressor that says, well, I can also tell you where are the coordinates for the bounding box for this object based on the whole image. And this was a big improvement over RCNN because, well, mainly it was a lot faster, but also it had higher detection accuracy. However, it still had the problem that you need this secondary algorithm that is proposing regions for the convolutional network to classify. So there was an interesting response to this algorithm, which was called YOLO, which is you only look once. And the really interesting thing about YOLO, other than the papers are hilarious to read, is that it could recognize as many objects as you wanted inside an image with one single pass of the network. So that allowed a great speed up in training and detection, because instead of having to pass several times over an image to find all the bounding boxes and find and classify all the objects, they proposed this architecture where you divide your image in different subsections, and then your network learns to find bounding boxes in those regions and also tell you which object is in those regions. So it is a pretty big network. They have the whole architecture here, but it is fully integrated. So the big step forward with YOLO was that you no longer needed several different algorithms to find all the bits of information. So YOLO passes once over the image, and it finds the bounding boxes for the objects, and it can also classify the objects. Of course, YOLO was updated, and in their own fashion, they called it better, faster, stronger. And I can't remember what was the update here, but basically they make better bounding boxes. And there is a final paper for YOLO, which is an incremental improvement. I think that if you read just the introduction to this paper, you can see what's the sort of spirit of this of Joseph Redman writing these papers. But this is just a small improvement. So this YOLO v2 is one of the most used algorithms for object segmentation and detection. And the final response, or the latest response that we've had, is faster RCNN. So faster RCNN, as you might imagine, is a faster version of fast RCNN. And what they did is they said, well, let's get rid of the region proposal algorithm. Okay, so instead of using a separate algorithm for region proposal, and a bit in YOLO fashion, they said, okay, let's integrate the whole thing so we can train the whole system end to end. So they proposed this region proposal network. And what the region proposal network is if you remember from fast RCNN, we have this convolutional layer here that produces convolutional features that will then be used to predict which objects are in there and where those objects are. So they take those convolutional layers and the last few layers, they link them to a separate network. And what this separate network has to do is find proposals for regions. So now it's all integrated end to end, and you don't need a separate algorithm to propose regions. So what this is a very clever approach, because what it does is you no longer need to be concerned with drawing your own regions. You have your system, which it's basically all based on convolutions all the way. So it's convolutional layers all the way down. And the system itself proposes the regions, and then the system itself does the pooling and then does the classification and regression for the two tasks. So in the context of object segmentation and classification, the part that converts the image into a set of convolutional features is what they call the backbone. And you can do several, like you can change this. You can use VGG 16, you can use ResNet 101. So you can change this fairly easily, as long as it's a convolutional network, because the region proposal network needs to leverage on those convolution to then make region proposals. And again, so what comes afterwards is also quite flexible. You can use fully connected layers, or you can add another convolutional layer on top. You can add your regression algorithms. So this is currently the state of the art for image segmentation. And again, if you stay till the end, just say if you want us to go a bit more into detail into these algorithms, and we'll be more than happy to do so. There is a fairly, well, it's now a bit old, but it sort of explains how convolutional networks work in this whole image segmentation. And again, with the names, Return of the Devil in the Details. You can also go to this paper if you want to see what are the bases of all these new approaches. So back to our paper. After we have seen all the architectures and how they work and how they're structured, then we can see the actual contributions of these papers, which seem minor, but they are actually, in my opinion, they are quite clever. And they're trying to tackle another problem in image segmentation and recognition, which is that sometimes you have classes that are extremely rare. So in a full data set, you may have 10 instances of the class. And this is a problem in other areas of machine learning, but it is a particularly big problem in image segmentation. So this data set called Elvis, which is by Facebook, I think. Yes, by Facebook AI Research. They have 160,000 images, and some of the objects only have 10 instances in a 160,000 image dataset. So you can imagine how hard it would be for a machine learning model to learn from that. So there are a few approaches to this. The most common ones are meta learning, where you learn a good set of parameters to learn from small classes. And there are fine-tuning approaches, which is what this paper does. So what you see here, which is the architecture, well, they don't propose a new architecture. This is just fast RNN, faster RCNN. And they propose a couple of clever things. So the first thing that they propose is to do a two-stage fine-tuning of this whole faster RCNN. The first one is with abundant images. So they train faster RCNN as it should be trained normally. And the second stage is just fine-tuning the classifier and regressor parts of the faster RCNN. And that uses a balanced data set with the novel data, which are all the data with all the examples with few, so all the objects with few examples, and some of the base images, but it is a balanced data set. And the other interesting thing that they propose is that this box classifier, instead of making it a fully connected network, they make that classification based on cosine similarity. And of course, the reason you can do cosine similarity here is because you're reducing massively the size of your data set. And yeah, so that is in a nutshell the contribution that they make. They speak a bit about the intuition behind what they're doing and how they train it, but I feel like this is all very standard. So maybe we can look at the cosine similarity is the only funny thing in the cosine similarity is that, so if you think of this box classifier here, it is a cosine similarity with trainable weights. So what these weights, so what this is going to give you is the similarity between one feature so one example that has gone through the whole network in feature space, and some learnable weights that you can use to train your network. And there's a scaling factor, which they don't give much intuition on why. I imagine it's just to introduce another tunable parameter to modify, to understand how the accuracy works with respect to a similarity. And they say they fixed it to 20, which seems to give them full results. As usual, it's good that they give an implementation. So if you go to the paper, you can go to GitHub and see the few shot detection algorithm. But so the big question is, does it work? And to find out if it works, they make a couple of experiments. Of course, they use YOLO, which is the YOLO v2 that we spoke about before. And they use the faster RCNN with different settings. One is just training everything all together. The other one is doing fine tuning, but fine tuning the whole architecture. Fine tuning just the last layers of faster RCNN. And the other one is fine tuning, but with fine tuning the whole architecture. And they use an interesting metric. So one of their arguments is that most of these approaches, they report the average precision on the training set, but they do not show if their approaches can retain accuracy in the base set as well. So they propose to use this average precision on the base set as well to compare algorithms, which I find quite interesting. And then they repeat this fine tuning several times. So they report the mean average precision for all classes, which again seems to be just for thoroughness. And the initial results are, well, of course, that they produce state-of-the-art results on all the novel sets. And what is quite interesting is that they produce what you would call acceptable results, even with one shot. So they only get one image for the fine tuning representing these rare objects, and they can still detect them with 40% accuracy, which is quite impressive, given that, for example, YOLO doesn't get anything until it gets 3 shots, and even with 10 shots, it it does quite poorly. It gets better after some fine tuning, so after fine tuning the whole architecture, but still it's nothing like what these guys are proposing. And even more interestingly is that when you have few shots, cosine similarity seems to work a lot better than a fully connected layer. This drops as you have more examples. I guess that is to be expected because, because of course, if you give a fully connected layer more shots, it's going to find richer features. Eventually, it might even learn the cosine similarity function. But this is very interesting. I guess it makes sense that cosine similarity will work with few examples because I guess similar classes, rare classes are going to look similar in different bounding boxes. So this cosine similarity, to me, it makes sense. But it is a very interesting improvement over all these state-of-the-art methods, which basically don't work on rare data sets. Then with regards to what I was saying before about that base average precision, it's also quite interesting to show that there is a drop in precision, but there is a significant gain in precision in the new classes, right? So even if you take the state-of-the-art methods, they can still retain some precision, but they don't reach as much. So this one is probably the best compromise possible between base precision and precision in the new rare classes. And then as you get more shots, you can see that the more shots to fine tune, you can see that the decrease in accuracy is not as significant as the increase in precision. Okay, so could you explain again how the cosine similarity is used in the prediction process? Yes, of course. So in this box classifier, which is the one that says, we have a raised hand. So just give me one moment and I'll give you, and I'll allow you to speak. So in this box classifier, which is the one that says the region of interest X contains this object or animal. So normally this is a fully connected layer. What they do instead is they replace that with a cosine similarity. Let's call it a trainable cosine similarity, where these weights can be trained. And oh, maybe I didn't say before, then they threshold it. So they threshold it at 50 or 75. And they say if this cosine similarity is higher than 50 for X class, then that is the predicted class. I hope that answers the question. Okay, Krish. Hello. You're muted at the moment, so. Oh, if you don't want to speak. Okay, I'll just. Okay. Okay, I hope that explains for the cosine. Okay, I hope that explains for the cosine similarity. So yeah. So yes, I guess when you have few classes, this using cosine similarity, when you have few examples using cosine similarity is already giving you, let's call it a pre-trained model on how to identify classes, which is the whole purpose of this, is to leverage where you can, so you don't have to train as much because you don't have many shots. Yeah. So the final observation that I had on this particular table is that you can see that, of course, the best way to get base accuracy is just to train the base classifier, but then you get very poor accuracy on the very poor precision on the new classes. So yeah, sorry. Related to the cosine similarity question when they say AP50 is they measure precision thresholding similarity at 50%, at 50, yeah, 50%. Yeah, so in a nutshell, it is an interesting method to find, to identify objects in a few shot environment. Well, they also show that it is very consistent, that their method is very consistent. Of course, as you force the similarity to be higher, your precision becomes lower. So basically at AP50, you're rejecting a number of examples which are not similar to anything, so you're refusing to predict. But as you make that threshold larger, you reach the average precision of the whole method, which is which is around 40%, which is what we see here. Okay. Yeah. Okay. Sorry, what is, and yeah, and so they made experiments on all these data sets because they have different properties. What's interesting about the COCO data set is that it has these extremely rare classes, which are only present something in less than 10 examples in the whole data set. So, so they show that, well, the average precision is low, but it is still higher than on every other method that they could think of. And so the final question, which, I mean, so the paper goes on and on speaking about precision in the different data sets. I think the story is the same for most the whole, for the whole paper, but I would like to open the discussion after this, which is my final question was, well, okay, you can detect objects very well, but how good are those bounding boxes? And this is where the funny results come, because, well, you can see, of course, that it is classifying this dog as a bear, or these squirrel. Are these squirrels or kangaroos? Well, or these bunnies as bears as well. So this is mostly a qualitative assessment. They don't make a thorough assessment on how good the coordinates are. But you can see that it does have some areas where it can improve in the bounding boxes. Yeah, so this is mostly the spirit of the paper is, well, how do we adapt this faster RCNN to work in a few shot learning environment? They seem to achieve good results with very simple methods. So it's an interesting way to approach this problem. So, are there any questions about the paper? Someone would like to speak, join the discussion? Mm-hmm. Okay, cool. So quick paper. So I'll just stop the recording.